There we go. Okay, so the first thing I need you to be able to recognize when you look at a number is the precision of it. The precision of it. Because anything that is counted is infinitely precise. If we count how many people are in this room, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, we mean exactly 18, right? If we say there's 18 people in this room, we don't mean that there might be 17 and a half. All right, we use that. There's no such thing as half a person. That doesn't make any sense. We don't mean 18.35, right? We mean precisely 18. When we count, we're dealing with numbers that are integer values, if we're speaking like a mathematician, right? In other words, they are exact. But anything that is measured is approximate. For example, if you were to take even a very precise measuring tool, right? Like this here can measure things, and this is, just a decent set of calipers. I think it's maybe $40, $50, but it can tell me that the length, or the width rather, of this is 11.71 millimeters. Now that's pretty precise, right? But could it measure something that was a different width, not exactly the same of this, and also give me 11.71? Well, sure, because all it means is that it's not 11.70 and it's not 11.72. But how many numbers satisfy that? Well, an infinite number, right? 11.708 would satisfy it, but so would 11.709. For that matter, so would 11.7085, and so would 11.7079. And do you say you could just keep going? There's an infinite set of numbers that all round to 11.71. Does that make sense? Just like if you're saying your age is 41, there's 365 different days where we can say that's true, right? And then in each of those days, there's 24 hours where you can say that's true. And within those 24 hours, there's 60 minutes, and so on and so forth. Does that mean it just keeps going? So when we measure a number, when we measure anything that isn't counted but rather measured, then it is always to the nearest something. Does that make sense? So let's look at these numbers. 23 mils. That is saying that we are measuring this to the closest what?
1?
Yeah, to the closest 1 milliliter, to the nearest 1 mil. And what values, what range does that actually represent? What values would give me a measurement of 23 mils? What's the smallest possible number that would measure 23 mils? Sorry? What about 22.8? What would that round to? Yeah. So we could say that's anywhere from 22.6 up to 23.4 kind of thing, right? Does that make sense? It's a range. We can argue about rounding specifics. In science, we typically round 1 through 4, always round down. 6 through 9, always round up. And then the 5. Does anyone know what we do in science by convention with 0.5s if we're rounding up or down? Even digit. So 22.5 would round to 22. 21.5 would also round to 22. That's the convention. We round 0.5s to the nearest even digit. That's a convention. Because if you do it at least that way, half the time it rounds up, half the time it rounds down. Otherwise, you're over-representing rounding up, right? So the way you were taught in elementary school is probably 0.5 always rounds up. But that actually means you're more likely to round up than round down when rounding, which imposes an error. Anyway, that's not the big deal right now. I want you to tell me the same thing for all these. All right, take 2 minutes and do that. 13.4 mils, what's that to the nearest of? And what range could that represent? All right, so take a minute and do that. Hi, how you doing? It's nice to see you. I did my phone, my SIM card died.
Oh.
So I've been, and then what I've learned is that it's been dying, so I didn't realize this. But it's been I won't be on the network for 6 hours, and then pops back on the network, right? So sorry about that. So anyway, what's up? Oh, great. we got? 13.4 mils. What's that to the nearest? It's to the nearest 0.1 milliliter, which means what basic range are we representing here? 13.35 would get us there, right? 3.5 would round to 13.4, all the way up to 13.45, right? And again, that represents a range. Does that kind of make sense? Any number in that range, anything that actually measures 13.44 mils is going to be measured as 13.4 if your tool goes to the nearest 0.1 mil. What about 123 meters? That's to the nearest 1 meter. That's right. And so the range there would be 122.6 up to 123.4, right? That's the range. Okay. Again, when we do analytical chemistry, I mean, not in this course, but if you take an analytical chemistry course, you actually have to do all your math with ranges. So every equation you do it with the smallest version of every number, and then you do it again with the biggest version of every number, and you report everything in ranges. We're not going to do that in this course, but that's how important these things are, actually, if you really need to know your tolerances. Does that make sense? It's what you have to do if you really need to know how precise you can be. This next one, what's it to the nearest? Maybe, or could be the nearest 50, could be the nearest 1, could be the nearest 10. Why don't we know with this one? What makes it tricky to know what this one's measured to? Yeah, zeros make this tricky. Because of those zeros, it's not immediately clear to me, is this what you would get if something actually weighed 100 grams and you measured it to the nearest gram? Yeah. The problem is this what you would get if something weighed 96 grams and you measure it to the nearest 10? Oh, shoot, yeah. Is this what you'd get if something weighed 51 grams and you measured it to the nearest 100? Yeah. Do you see the problem there? And it's not immediately clear. So with this one, we have to say it's not clear. And the reason why, nailed it exactly right. The zeros make it ambiguous. What's the word ambiguous mean? Ambiguous. Yeah, that's right. It makes it unclear. It could mean more than one thing. So in this case, it's hard to know, is this the nearest 1 gram, the nearest 10 grams, or the nearest 100 grams? And if you want to be really safe when you were doing calculations, like my thing where the guy said, hey, this thing is 8 feet wide, I made the assumption that this person had at least measured to the nearest inch. Whoops. Right? I was wrong. They hadn't. They just kind of said like, yeah, boom. Oh, look, it's about 8 feet. And I made a thing that was too wide. I had to take it back to my shop, and I had to adjust it. It ruined my week. And my pocketbook. Made me very unhappy. So, if you're going to be safe, what would you want to assume here? Unless somebody tells you otherwise. Are you going to assume that they were being really precise, or assume that they were speaking generally? You should assume generally, right? So the safe assumption would be to assume they're kind of talking to the nearest 100, right? If somebody tells you that they're 6 feet tall, they might mean that they are 6 feet 0 inches tall, or they might mean that they're roughly 6 feet tall. Do you know what I mean? And again, if you really had to use that measurement in a moment, you wouldn't want to use it assuming that they meant 6 feet 0.000 inches, right? Do you know what I mean? You're going to assume that they're speaking generally, And especially, if you went somewhere, say you're at like a concert, and you said, oh, wow, how many people here? And they said, 200 people. You wouldn't assume that that means that there's exactly 200 people, right? I mean, I wouldn't. I would assume they meant about 200 people, right? And especially if somebody was like, there's 20,000 people here. You probably wouldn't assume, oh my goodness, they counted and it was exactly 20,000, not 19,999 or 19,998. You would kind of naturally understand that that number is has the word about in front of it, right? Yeah, about 20,000 people. Does that kind of make sense? But if you went to someone and said, how many people are here? And they said 19,437. What does that tell you? It tells you that's precise. It tells you that they counted, right? They could still be wrong, but you wouldn't say, if you're trying to say, yeah, there's a lot of people here, you wouldn't say, oh my goodness, I think there's 19,437 people here. That's just not what we do, right? When we say a number that is specific, we understand that to mean that we've measured it carefully and precisely. And when we say a number that has a bunch of zeros on it, we know that often we do that to speak generally. Does that make sense? Same thing happens here. Zeros might mean exact, but they also might mean rounding. Because when we round, we introduce zeros, right? Does that make sense? So, what do we do with this? All right, well, the answer is sometimes we have to look at this and say, how many of these numbers are actually numbers that count, that they actually counted, and how many are just placeholders? And here it's obvious. There's 2 digits here, and both digits have obviously been counted, right? There's 3 digits here, and obviously all 3 digits have counted. There's 3 digits here, obviously all 3 have counted. But this one, we say, well, that's a 3-digit number, but I actually don't know if those zeros are numbers that have been carefully counted or if they're just placeholders. So if I'm in a fix, if I have to make the decision, I would look at this and say, really, I'm only confident that that 1 is a meaningful number, a significant number. Those zeros might be significant. Maybe they counted to the nearest person, or in this case, the nearest gram, but maybe they're just rounding. Does that feel okay? Back to this. Oh, I erased it. Back to my age thing. Okay, so let's look at some examples. What we're going to do is count how many of the digits are significant or meaningful. In other words, have been measured. This one's easy, but I'm going to give you the answers, and I want you to see if you can come up with the rules. We've already talked about a couple. So we have 3 digits here. Obviously, all 3 of those have been measured. So this number has 3 significant digits. I'm going to say that this one here has 1 significant digit. But then when I look at this one, I'm going to say that it has 4. When I look at this one, I'm going to say that it has only 1. But when I look at this number, I'm going to say that it has 4. When I look at this one, I'm going to say that it has 3 significant digits. And when I look at this one, I'm going to say that it has 6. I want you to take a look at that for a minute and see if you can puzzle out what our rule is then. First of all, the first rule is really, why was this one just immediate for me? I didn't even have to think about it. Yeah. So any digit that is not a 0 just always counts. The only thing we use as a placeholder is 0. So if it's not a 0, it's definitely not a placeholder. Does that make sense? Okay. So any non-zero number, I should say digit, is significant. But then here, for some reason, I said these zeros don't count. But then these zeros, I said they do count. Why? Yeah. Yeah. The answer is, if you look here, this makes sense, right? If you meant about 100, if you went to a concert and they said, oh my goodness, how many people are here? And somebody said, yeah, about 100. You'd understand that to mean about 100. If you went to a concert and they said, how many people are here? And they said 100.0. First of all, you'd be like, what's 0.2 of a person? But secondly, you would know that they're not just saying about, right? You know what I mean? Like if somebody says 100.0, they mean I have measured this. Any time we have zeros after a decimal place, as long as they're not the first 0, they count. So we're actually going to jump to this. Why did I only say 3 here? What are all of these zeros doing? They are clearly just placeholders. They're just showing us that we measured this 300, but it's not 300 mils, it's 300, and the scale we're using is 1/1,000,000th of a mil, so we have to use the decimal just to show the placeholder. So the first thing we say is any zeros before a non-zero aren't significant. Right? They're just placeholders. And if you think, if we look at an example there, if we said 0.00041, we would only count the 41, and we would ignore all those zeros. They're just placeholders. Does that make sense? These are placeholders. And these are significant. These have been measured. The obvious example of this is, like if I put 21, if I put zeros in front of it, does it change that number? No. They're just placeholders. They don't do anything. No hundreds, no thousands, no 10,000s. So any zeros before we get to the first non-zero, they don't count. The next thing we can say is like this number here, if I counted this and I counted that, I had to have counted everything in between, right? So zeros between non-zeros are always significant. So there we could have the example of 2003 or 20.14, or 20.14 would work, right? All of these count. The only time it's ambiguous is zeros after a non-zero when there's no decimal. Those are the only ones that are screwball-y where you don't know. And since we don't know, we assume that they don't count. Unless they tell us. If I said 100 grams to the nearest gram, then you would treat all three of these as significant. But if I just say 100 grams without telling you that it's to the nearest gram, then you have to assume that those zeros are just placeholders. So that's rule 4. Trailing zeros, when there's no decimal place, are not significant. And I'm going to shrink this down ever so slightly. I'm sorry if you've used your whole page up. Try highlighting it and just sort of shrink it down a bit like that. So for example, 200 or 1,300 or 13,000, we assume that these count, and unless we're told otherwise, we assume that these don't. Does that make sense? Sorry? Oh, I did. Oh, shoot. Well, that's okay. If you want to write them twice, you can. I'm not going to write them twice. And then the last rule, see, I outsmarted myself. That's not very hard. The last rule is that trailing zeros, not trawling, trailing zeros when there is a decimal place do count. Because why would you ever write 100.0 if you meant about 100? You wouldn't, right? Why would you ever write 100.000 if you meant about 100? You wouldn't, right? Does that make sense? Why would you write 1.300 and not 1.3? The answer must be that you're saying, I measured that. You would never waste the time to write those trailing zeros when there is a decimal place, right? So trailing zeros when there is a decimal place are significant. And the example there would be we could write 200, and you'll actually see this sometimes as 200 decimal. That actually now is telling me, oh, I want those to count. Or 200 decimal 0. Or 13.000. In all of those cases, all of the digits are significant. How's that feel? Kind of okay? We're going to get a lot of practice with this. I don't want you to think of it as rules to memorize. Some people really like rules. That's why I write them down. But it's actually, in my mind, more helpful if you just think of it as like if you were talking to somebody. Could you trust that every digit they told you was significant? If somebody said that is 134 grams, you would trust that they meant 134, not 133, not 132. You'd trust that that meant the nearest gram. Whereas if somebody said that's 130 grams, you'd have to say that 0, that's ambiguous. Maybe they just measured it to the nearest 10. They might mean 127. They might mean 132, right? Now, if they said it's 130 grams exactly, then they would mean that they count all three numbers. So I want you more often than not to come back to the rules. I don't think that's important. We're just going to talk about it a lot. Every time I write a number down between now and the end of this course, I'm going to ask you, how many significant digits is that? And I promise that when I do that 6,000 times, which true or false, you're going to get used to it. All right? I promise. I'm going to ask it about every single number we look at. All of them. All right? So now, what do we do when we multiply and divide? Listen. Your answer can't be more significant than the information you use to get it. Does that make sense? If I say every person in this room is going to get $22, all right? $22 per person. And then I say, how many people in the room? About 100. Do I know exactly how much money I need? No, right? Does that make sense? I only know that I need about $2,200, right? But I couldn't say that if I went to the bank and got exactly $2,200, I would have exactly the right amount of money, could I? Does that make sense? And these things can get really precise. If I said every person in this room is going to get $22.34 deposited to their account, right? And then say, how many people in the room? About 100, right? Could I say that definitively I'm going to spend $2,234? Can I trust that number? No. What would I have to say? I'd have to say, well, I've only measured this to one significant digit. I know it's going to be about $2,000, right? But I can't trust it'll be 2,200. Could it be 2,500? Well, sure, if there's 130 people, that'd be $2,600, right? Does that make sense? So I can only trust the first digit here because I only used one significant digit to get the answer. Does that make sense? So we're going to write that here. All right? For example, 22.34 times 100 equals 2,000. It does not equal 2,234. Why? Well, the answer is that when we just put it in our calculator, it's going to give us 2,234, but this is what we have to ask. How many significant digits does this have? 1, 2, 3, 4. Right? How many significant digits does this have? Well, we know the 1 must be significant, but the zeros are ambiguous, so we assume that they don't count. So this only has one significant digit, which means our answer must be rounded to one significant figure, which means we write this as 2,000. And if you leave it like this, you're assuming a precision that you don't actually have. You're assuming a precision that you don't actually have. And you can get into a lot of trouble in math, assuming a precision you don't actually have. So I'm going to give you guys a question. Let's say 3.514 times 2.78 divided by 92 times 1.107. And I want to know what the answer to that is. Now, you're going to need a calculator, presumably. I don't know how your 3.514 times tables are, but mine is pretty rusty. So use a calculator to get that answer, but then round it to the appropriate number of significant digits. All right, take a minute and do that. You got something for me? Cool. When we do this in our calculator, what does it give us? 3.5 times 2.7. I mean, now we should be roughly in the order of like 11.5. Divide by 92. 11 divided by 100. So that should be like on the order of 0.1 times 1 point-ish. So we should be in the 0.1 range. What do we get? 3.514 times 2.78 divided by 92 times 1.107, and we get 0.1175. Cool. So when we take it on our calculator, it's just going to tell us that the answer is 0.1175. And in math class, that would be the answer. In science class, that is definitively not the answer, because that does not imply the correct level of confidence. It doesn't imply the correct level of precision. So what we always do when you're multiplying, the rule is simple. Whatever your least significant number is, however, that is how significant your answer should be. Yeah. Hello. Please. Oh, bless you. Yeah. I would love just a black dark roast or whatever. And you know what? I have a cup of that. I don't have to. Okay. Yeah, that'd be great. Thank you so much. Oh, I'm so excited right now. You have no idea. It's making me so happy. Sorry. All right. So, how many significant digits does this have? 4. How do we know 4? Nice, easy one, right? Right? When there's no zeros, they're all significant, right? So 4 sig figs there. How many sig figs here? 3 sig figs. Good. How many here?
2.
Okay. How many here?
4.
What about that 0?
It's in between.
Yeah, it's in the middle. So it's got to be 4. So now, what's the least significant? 2. Okay. So that is what we have to round this to. And when you're doing that, remember, you're not working this way. You're working this way, right? That is going to be significant. That's going to be significant. And then these are not. But again, it doesn't mean you just erase them. We're still rounding. So what will this round to? 0.12 is the correct answer. And 0.1175 is an incorrect answer. And in this course, I'm going to treat it as an incorrect answer. Right? The expectation is not just that you'll shove it into your calculator and not think. You're going to shove it into your calculator, you're going to write the number down, and you're going to pause and look at the question and say, how confident can my answer be? Because if you're an organic chemist, or if you're, and I'll tell you, I can tell you a real world, very expensive example of this. When I worked at Ravine Winery, I worked in the restaurant. I managed the restaurant. I didn't work in wine production, but it was a small establishment, so I knew everyone. And on bottling days, they used to hire this mobile truck to come in, and we would bottle all the wine. It was super cool. If you have a chance at any point to do something like that, it's really neat. It's like a transformer. This truck comes in, and then all of a sudden, vroom, vroom, and it's this whole thing, and you shove the pump down into your vats of wine, and it puts them into bottles for you. It labels them. It puts the caps on the bottles. Bless you. Thank you so much. Oh, you've made my day. Thank you very much.
Cheers of your student.
Right? See them? I'll them all crying by the end of this period. See what I can do. But I'll settle for one of them. So that's not even true. I didn't buy this mug, but I do find it whimsical. Sorry? It was just the one in front. A few years ago, a student bought me, what did it say now? I can't remember what it said. I'm going to remember what it said. I'm going to tell you. I remember it being funny, though. Anyway, it fell and broke, so now I don't have it. Okay, so what was I saying? Oh, yeah. So we bottle all this wine, but when they bottle them, they label them, right? So they get put in the bottle, the label gets put them, and by law in Ontario, your label has to say how much alcohol is in your wine, percentage-wise, right? That's a law. Any alcoholic beverage has to say on it what percentage it is. And ours said 14% alcohol by volume on this particular bottle of wine. We sent it off to the LCBO for testing, and it came back at 13%. And that meant that we weren't allowed to sell our wine because the label wasn't true. So we had to peel the label off, 1,224 bottles of wine, clean the gunk off those bottles, and then apply new labels. It was a very expensive mistake, and it was a rounding error, right? Because the machine spit out the number like 4181, whatever. And it was just a rounding error, either on our end or maybe on the LCBO's end. It doesn't matter. What matters is they tested it twice. They got a number that was different than ours, and they sent us a memo saying, you can't sell this wine, so if you want, you can destroy it or you can relabel it. So we relabeled it. Very expensive. Not a mistake you want to make. And again, I'm not even confident that we made the mistake. Maybe their lab did. It didn't matter. Does that make sense? Digits matter. So, a few things to know. Note that whole numbers have an infinite number of significant digits. Let's use an example. If a hairdryer uses 1.2 kilowatts of power, then 2 hairdryers would use 2.4. Can we all agree that's true? So listen, when we do that and we say 1.2 kilowatts, which is the power of one hairdryer, times 2 equals 2.4, don't the rules say that I should have to change this to just 2? And the answer is no. This is 2 significant figures, but this is infinite. And the reason it's infinite is because it's counted. Does that make sense? Counting numbers are infinitely significant. When we say those 2 hairdryers, we definitely don't mean that I bought 1.96 hairdryers. What would that mean? That wouldn't mean anything. It's a meaningless statement, right? And we don't mean that I bought 2.05 hairdryers. Because again, what does that mean? It doesn't mean anything. So if something is counted, it is infinitely significant, which means our answer would then be not 2.4, 2 significant figures, because the number 2 is smaller than infinity. Yes? Infinite and 1 would be what you're multiplying. So the lowest one would be 1. Does that make sense? That was a great question, by the way. So yeah, a 5-digit counted number is still counted, which means it's still infinitely significant. And we're always, when multiplying, going with the least. Let's try this as an example. Let's try, this isn't the counted thing, all right? This is just practice in general. I'm going to give you 3 of them. Do I have time? Yeah, I got lots of time. No, tons of, well, we're good. I'll give you 2 of them. Let's do 2.005 times 120 times 13.4. And let's do 143 divided by 2.15 times 100. And then we'll talk. Nothing counted here, by the way. These are all measured values. And like, where did that? All right, this top one. 2 times 120 is 240. 240 times 10 is 2400. 3 times 240 is 720. So that should be on the order of like 3100. Cool. How much? 32. 32. 4. Okay. Exactly. Should be. 0.04. Okay, as given. Cool. So that is what it equals when we just shove it into our calculator. Cool. Now, how many sig figs here?
4.
Yep, all 4. Absolutely. How many sig figs here?
2.
You got to assume 2. Good. Here? 3 sig figs. And so that's going to be sig fig. That's going to be a sig fig. That's going to be a sig fig. These are not. Which means that the answer is 322. Pretty sure it's 322 because those 3 digits are significant. And we said all of those digits aren't significant, so I wrote down the significant ones, and we can move on to the next question. Oh, you're right. I'm sorry. The answer is 32. There we go. Because that's also not significant. Sorry? For all, okay. Oh, I need the decimal, though. There we go. Okay, that's it. Okay, so like that.
Don't remove the decimal.
Don't remove the decimal. Okay, I won't. I promise. Oh, okay. Do remove. You see how this is confusing, though, right? You told me one thing, then you tell me the exact opposite. How's that now?
Yeah, okay.
Good. Okay. Listen, this is my only joy in life, all right? That's not true. Okay, how's that? All right, 143 divided by 2 is going to be 70 times 100 is going to be 7,000, right?
For the first one, will we round down to 31?
No, you never round down, right? The question is, right, you never round down. This number will never lower because we're at least at 3,200. The question is, are we close enough to the next 100 that it would round up, right? So it'll either stay at 2 or bump up to a 3. That's right. Yeah, you can never round a number down the way we count, right? We count ascendingly in digits. So yeah, and I don't think I even need to do any, I don't think I have to do any math here. The reason I don't think, or like any calculator math here, because I'm pretty confident that's the answer. And this is how many sig figs? 3 sig figs. This is 3 sig figs. But this is 1 sig fig. So how'd I do? Yeah? What's the answer if you shove it into your calculator?
6651.
6651? Yeah. Right. But the answer is 7,000. And the answer is 7,000 because that's significant and these are not. Does that make sense? Yeah.
Isn't 120 and 100 like a whole lot?
Sorry?
Wouldn't 120 and 100
Again, I've told you here, the measured values. They're whole numbers, but whole numbers doesn't mean all significant. Again, if you put something on a scale, it may read 100. That doesn't mean that it counted out the number of grams. That doesn't mean anything. It's still a measured value. Does that make sense? And that's where you're going to make most of your mistakes, by the way. That's where people make the most mistakes. They see that and they go, oh, 100, 3 sig figs. But you cannot assume that that's 100 exactly. If they rounded, would 98 turn into 100? Would 111 turn into 100 if they rounded to the nearest 100? Yeah, right? So you just don't know. Yes?
So for the 7,000 one, on the calculator, it was like 6.
Yeah, let's write what it equaled from the calculator. So it is 6,651.14, someone said? 1.6, right. Okay, there we go. Okay, so now when we go to round here, the question is just, is this 6,000 or is it closer to 7,000? So is it 6,000 or is it closer to 7,000? It's closer to 7,000, right? 6,600 is closer to being 7,000 than it is to being 6,000. That's right. Yeah, does that make sense? And obviously, I can't leave the answer as 7 because 7 and 7,000 are very different, right? Now, by the way, a better way to write this, these are both unclear. You know what a better way would be? 3.2 times 10 to the exponent 1, 2, 3. That's a much better way to write that because now it clearly has how many sig figs? 2. Unambiguously, right? What's the better way to write this? 7 times 10 to the 3 as well, right? Scientific notation, never ambiguous. Because if you don't want, right? Because we don't need zeros as placeholders. So if you don't want to measure it, you don't put, right? So if this had been written as 1.00 times 10 to the 2, we would know both those zeros count. Versus if it was 1.0 times 10 to the 2, we'd know it's the nearest 10. If it was 1 times 10 to the 2, we know it's the nearest 100. So if we just put numbers in scientific notation, then we know exactly how significant they are. That's part of why we use scientific notation. All right. Now, what about when we're adding? Adding is a different rule. And if you think about it, it makes sense. Ready? Look here. Don't write this down. Just think this. Let's say that I, hypothetically, weigh 201 kilograms. No, that would be a lot. 101 kilograms. It's still a lot, but it's less of a lot. Okay, I weigh 101 kilograms. How many sig figs is that? 3 sig figs. Okay. Now let's say I weigh this clip here, and I find that it weighs 0.215 kilograms. That's unrealistic. It weighs 0.0215 kilograms. All right? I have measured that on that there, right? Does that make sense? And let's do a different example. Let's say, ready? I screwed up my example. Sorry, I screwed up my example. Ready? Let's say I take off my boots. I'm wearing big, heavy boots, work boots, and I take them off, and it turns out they weigh 2.156 kilograms. How many sig figs is that? 1, 2, 3, 4 sig figs, right? Okay. When I go to subtract, I'm going to get, somebody do that math? I'm going to get 98 point something, right? Somebody do it? Come on.
98.8.
Was it 844? I could have done that, but I didn't. Okay, how many of these digits are significant? And here, you might be tempted to say, we should keep these 3. Does that make sense? Because you might think, oh, we do the same rule, the least number of significant figures, right? And so you might be tempted to say, oh, now I must weigh 98.8 kilograms, right? The problem with that is, that implies that I knew that I weighed 101.0 here. Because if I'd weighed 101.2 here, would I have got 98.8? No, I actually would have gotten 99.0. And if I had weighed 101.3, I'd have gotten 99.1. Pay attention, because this is subtle, but it's important. With adding and subtracting, the rules are different. We don't use sig figs in adding and subtracting. We use what decimal place. That is so important, and it's an easy mistake to make. So we do not use significant digits. We use the number of decimal places. Not the number of decimal places. What we really do is like the place value, because it doesn't have to be after the decimal. It could be the tens column or the hundreds or the thousands, but it could also be the thousandths or the 10,000ths. We use the place value of, so the least significant place value is the example. So this is 2 decimal places. That's 1 decimal place. This is 4 decimal places. That's 1 decimal places. But keep in mind, this is the tens column, right? And the next one, if I did 1100, that would be the hundreds column. Does that make sense? It's just the place value. Is it in the second decimal place, the first decimal place, the fourth decimal place? Or is it the tens, or is it the hundreds? You go with the least significant one of those when you add or subtract. So let's look at 2 examples here. If we said 34.25 plus 103, what would we get? If we said 104.7 plus 23.65, what do we get? Do both of those. Okay, this first one is trivial. 100 plus no more hundreds is 100. No tens plus 30 is 30, so 130. 3 plus 4 is 7, so that's 137. And then 0.25. But, again, this here could have been 103.1 or 103.2 or 102.8. So we can only trust. Here, we go to the second decimal place, right? But here, we only go to the ones. Which of those is least significant or least precise? Ones are less precise than the second decimal. So where do we have to round this to? The ones column. All right? So that's what you do when you add or subtract. When you multiply, you count significant digits. But when you add and subtract, you look at place value. The least precise place value. So this will actually equal what? 137. Does that make sense? Sorry? That's right. That's right. It's the nearest one. So our answer can't have any decimal places. It's to the nearest one. Does that make sense? You have to work the other way. So think of it this way. Ready? Let's say I weigh 101 kilograms. All right? And let's say that Quentin uses the same scale and he weighs 80 kilograms. 81, just to make it easy. So if you put us together, we would weigh 182 kilograms, right? Okay. Well, let's say that on his way over to me, he picks up something that he knows weighs 0.25 kilograms. When you put the 3 things together now, can we confidently say that me, Quentin, and the thing he picked up weigh 181.25 kilograms? Of course not, because I might have weighed 101.2, and he might have weighed 81.3. So we can't trust that 0.25 is changing us here. So with adding and subtracting, we don't count significant digits. We say, what is the least precise number that we're working with? This is to the nearest 1, whereas this is to the second decimal place. Which one of those is less precise? To the nearest 1. So our answer is also going to get rounded to the nearest 1. So the least precise value. All right, what about this here? Again, this is fairly straightforward. It's going to have a 5 on the end. 7 and 6 is 13. Carry the 1. 4 and 3 is 7, so that's going to be an 8. 0 and 2 is 2, so 128.35. No? What did I screw up? Oh, okay, yeah, we'll get there. Right, so that's good. So now, what is this to? This is to the nearest first decimal place, right? We call that the 10th, but people tend to get that screwed up. So I'm just going to say the first decimal. This is measured to the nearest second decimal place, right? To the hundredths column. So which one of those is less precise? Yeah, 1 decimal place. So we got to round here. So this would be 128.4. Very good. 5 gets rounded to the nearest whole number, or the even number, rather. How's that feel? Not too bad? And again, I'm actually not going to give you a big homework sheet for this today. We'll do a little bit of practice with it coming. But where we're going to practice it most isn't in isolation. We're going to practice it while we're doing chemistry. Does that make sense? And you're actually going to find that when you practice it while you're doing chemistry, it's a lot easier to learn than trying to memorize it as a bunch of rules. And again, ask Baskerville. Every single question we do, I'm going to break out my little blue pen and say, how many sig figs is this? How many sig figs is that? Great. When we multiply them, what do we get? Or if we're adding, what decimal place is this measured to? What decimal place is that measured to? And you're going to hear it. Yeah, you're going to hear it over and over again. Now listen. Shh. Look at me. I am going to try to teach you that your best bet is not to do intermediate answers. I'm going to teach you, I think, that it is always best to use your calculator exactly once and do all of the calculations in one big long stretch. But if you do pause in the middle, always keep an extra digit until your final answer, or you will start to introduce rounding errors. Does that make sense? So we keep an extra digit until we go to the end. The 2 big sins of significant digits. 1, writing more digits in any of your answers than are justified by the final number of digits in the data. And then rounding, this is what happens all the time. They round off in the middle, and then they do the first one at the end. So they do a first calculation, round it to 1 decimal place, and then the final answer goes to 5 decimal places. Well, that doesn't work, right? So the main thing is, I'm going to try to convince you that you should only ever touch your calculator once in a question. Just do it all. Just do the whole thing. But sometimes we got to do it in steps. And if you have to do it in steps, we keep a few extra digits, but we keep track of how many our final answer should have. Yeah. All right, guys, we'll see you tomorrow. Have a wonderful day. Be kind to one another. Don't do anything Annie wouldn't do. You'll notice that I no longer say Tamari or library. And that serves as a bit of a shibboleth for my generation. Because you know who were Simpsons watchers and who weren't.